All right, welcome to the video on circle proof practice. The purpose of this, of course, is to give you some experience and some practice writing proofs that involve circles so that you become more familiar and comfortable with the entire process, which can be difficult at times. All right, so let's jump right in. Number one says we're given all those chords. We could tell from looking at the picture that they're chords. Remember that a chord is any segment whose endpoints are on the circle. Notice what it is exactly that they're asking us to prove. They're asking us to prove that the products of a couple segments are equal to each other. Anytime I see products, I should think to myself, similar triangles. We're going to get these products by cross multiplying the sides that we get in a proportion, and the way that we establish that sides are in proportion is to show that two triangles are similar. So as soon as I see those products in the proof, I think to myself, or it should be a key for you to think for yourself, to use similar triangles. Of course, I need to make sure that I use triangles that have those sides in them. So I'm going to start by taking a look here at which sides exactly it is referring to. So side AE, side EB, the next one is in a different triangle. I'm going to color code it with a different color. Side CE, the third one, is in the same triangle as side EB, so I'm going to color code that the same color. And then the last one, side ED, is in the same triangle as the first one. I'm going to color code it the first or the same color. And now looking at the picture, I can see pretty clearly exactly which two triangles it is I need to prove similar. Now I know similar triangles, the easiest way to prove them similar is to show that they contain a pair of congruent angles. So I'm going to start by going ahead and looking for a pair of congruent angles. The easy one that everybody's going to see, or at least I hope that everybody's going to see, is that pair of vertical angles at point E. So that's one pair of relatively easy vertical angles to find. The other angles are a little bit more challenging. I'm going to start by taking a look at arc DB down at the bottom of my circle. I'm going to color code that purple. Arc DB has a couple of inscribed angles that intercept it. If I look backwards from arc DB, I see that one of the angles that intercepts that arc is inscribed angle A. And if I look backwards in the other direction and follow those sides back, I find that another inscribed angle that intercepts that same purple arc is arc C. And anytime I have two inscribed angles that both intercept the same arc, I know that those inscribed angles have to be congruent. Likewise, I could have started by looking at this blue arc up at the top, arc AC, and had I worked backwards from there, I would have found another pair of inscribed angles that share that arc, angles D and B, and they therefore have to be congruent as well. So we really have now three pairs of congruent angles. We only need two. I'm going to use the two that come from the inscribed angles just because that way I'll have one less step to write in my proof. But if you feel more comfortable writing about the vertical angles, then by all means feel free to do that. So I'm going to go ahead and start out by saying that angle A is congruent to angle C. And since angle D is congruent to angle B for the same reason, I'm going to put them in the same step. And my reason is going to be that inscribed angles, notice that I describe exactly what kind of angles they are. I don't just say angles. Inscribed angles that intercept the same arc are congruent. And from this point forward, this proof becomes just like any other that you've written. It doesn't have anything else to do with circles. When I go to name my similar triangles, I'm going to make sure that I name them in the correct order in such a way that the congruent parts correspond. So triangle AED is similar to triangle CEB, and that of course is by angle-angle similarity. And there are two properties of similar triangles that you need to remember. The first is that corresponding angles are congruent. The second is that corresponding sides are in proportion. The one that we want to use here, of course, deals with those corresponding sides. I'm going to pull the pairs of corresponding sides right from up here in my proof. So AE is going to be one pair. I'm going to want to cross multiply that with EB. And the side that corresponds with AE in the red triangle is CE. And that corresponds with EB is going to be ED. So I knew that these pairs of sides were in proportion because they're corresponding sides in the similar triangles. So I'm going to say similar triangles have corresponding sides that are in proportion. And then the last thing that I'm going to do is I'm going to take the numbers in my, or the sides in my proportion, and I'm going to cross multiply them. So the product in going in one direction has to be equal to the product going in the opposite direction. You can be fancy and say the product of the means is equal to the product of the extremes. I'm going to keep it simple with what you're familiar with and just say cross multiplication. And again, you can see that with the exception of that very first step where we used the inscribed angles, that proof is exactly like the ones that we wrote back in the unit that we did on similar triangles. All right, a new theorem up at the top of the next page says any angle inscribed in a semicircle has to be a right angle. I want to show you why this works, or why it has to be so, because if you understand how come it works, you'll be more inclined to remember the theorem. So let's take a semicircle. Semicircle is going to be half of a circle, and let's inscribe an angle in it. So an inscribed angle, by definition, has to have its vertex on the circle, and we're going to inscribe it in the semicircle, meaning that the semicircle is going to be the arc that he intercepts. Well, the degree measure of this arc, because he's a semicircle, is going to have to be 180. Because this guy here is an inscribed angle, his degree measure is going to have to be half that of the arc he intercepts, or half that of the 180 degrees, making his degree measure equal to 90, and forcing him, therefore, to be a right angle. So again, if you connect everything that you know about inscribed angles and semicircles, it makes sense that that angle would have to be a right angle. All right, well, you know what's coming next now, don't you? Let's go ahead and get into this one. Circle O with diameter CH. CH is perpendicular to TO, and they want us to prove that those two ratios are equal to each other. So with that said, I guess I'm going to start by going ahead and marking all my givens. So CH perpendicular to TO. And then, like I did in the problem before, I'm going to start by taking the sides that are in this proportion, and I'm going to color code them so that I can determine exactly which two triangles it is that I want to prove similar to each other. So there's my first side, CT. My second side is CH. That's in the same triangle as the first one, so I'm going to color code it the same color. TO, I'm going to make purple, different triangle, so different color. And then TH is in the same triangle as TO, so I'm going to color code that one purple. And again, I can fill that in now, and I know exactly which two triangles it is I'm trying to prove similar to each other. All right, so I got the blue one, the big one, and then the little purple guy. Well, if I take a look down here at point H, that's a shared angle. That's going to be a reflexive property. There's one pair of angles out of the way pretty quickly. The other thing I'm going to take a look at is I'm going to take a look at this semicircle from C to H. And I'm looking for a right angle. And the reason I know I'm looking for a right angle is because I've already got one here at point O. And that's a semicircle. Any angle that's inscribed in that semicircle is going to have to be a right angle. Well, if you look over here, this angle CTH is inscribed inside that semicircle. He intercepts the semicircle. He's going to have to be a right angle. So I've got a red angle in the blue triangle congruent to a red angle in the purple triangle. I've got the angles at H congruent in both triangles. That's going to make my triangles similar. So I'm going to go ahead and start out by talking about circle O. And there's my abbreviation for circle. The fact that CH is a diameter is important because that tells us where the semicircle is. So I'm going to include that in my givens. All right. So we are off and going. It really doesn't matter what order I get these into the proof as long as I get them in there somewhere. Somewhere in my proof, I need to talk about angle H being congruent to angle H. I need to talk about angle TOH being congruent to angle CTH. And again, it doesn't matter which order I get them in there as long as I get them both in. I guess I'm going to start by talking about these perpendicular lines. So that's going to make angle TOH be a right angle. I know that because perpendicular lines make right angles. The other thing I know from this given that gives me my inscribed angle, gives me my semicircle, my inscribed angle at point T. That tells me that angle CTH is a right angle. And that's because an angle inscribed in a semicircle is a right angle. Sorry about that, folks. So I've got two right angles. They therefore have to be congruent to each other. So there is one pair of congruent angles. The second pair that I need to get into my proof is that pair at point H. Well, that angle is going to be congruent to itself by the reflexive property. It's the same angle in the blue triangle as it is in the purple triangle. So there's my second pair of angles. And anytime you have two angles in one triangle congruent to two angles in the other, we know the triangles need to be similar. So triangle CTH is similar to, and I've got to be very careful again about the way that I name my vertices. So T was the right angle, so I want to match that up with angle O. H corresponds in both, and therefore my first vertex of the smaller triangle has to be T. So that's angle-angle similarity. And now that the triangles are similar, I know that all their corresponding sides have to be in proportion. So my last step here is going to be that proportion. So when I compare CT and CH, it has to be the same as when I compare TO and TH. And I'm just going to say when triangles are similar, corresponding sides are in proportion. You could say have equal ratio. So I would hope that this whole proofwriting process regarding circles is starting to feel a little bit more familiar and a little bit more comfortable. But as always, if you have questions or if there are things that I talked about in the video that didn't make any sense to you, please make a note in your notes right now so that you'll remember to ask me about it the next time that you come to class.